So as we've learned refrigeration, we understand that the refrigerant boiling or changing state from a liquid to a vapor absorbs a massive amount of heat. A massive amount of BTUs are being absorbed into the refrigerant where it's changing state. That saturated state of that refrigerant is so very important. So if we have the majority of our evaporator coil at saturation, at latent heat, it's absorbing a massive amount of BTUs. But if my saturation is only taking place down here, I'm absorbing very little BTU. All of this will be superheated, which is easy to measure, but it's very little BTUs overall. Another thing is the temperature of the air is going to affect my suction pressure. As the temperature of the air goes up, my suction pressure goes up, and as the temperature of the air drops, my suction pressure also drops. So of all the metering devices that we've talked about, the fixed orifice had the most variables. The fixed orifice metering device was just simply a hole. So as the outdoor temperature goes up, the pressure goes up. So there's more pressure pushing more liquid refrigerant into my evaporator coil. That will affect my suction pressure as well as how much liquid I have to work with. Then as the outdoor temperature drops, I have less pressure pushing less refrigerant into my evaporator coil. I end up with less suction pressure and I end up with less liquid refrigerant to work with. On top of that, we have the factor of the temperature of the air and the humidity of the air affecting how fast or how slow that refrigerant boils away. If I have a very large heat load, my refrigerant can boil away down here very quickly and I have a whole lot of superheated vapor. And if I have a very low heat load, I could end up with a very small amount of superheat and a whole lot of saturated liquid mixture. That's why our target superheat for a fixed orifice metering device can sometimes have a very high number of superheat, meaning very little saturation, or it could end up with a very low amount of superheat, meaning we have a whole lot of saturation, because all these conditions affect it. But it's the saturation, it's the magic of that refrigerant boiling from a liquid to vapor. Our pressures are going to be changing all the time. Then we moved over to a thermostatic expansion valve and an electronic expansion valve. Those valves simplified things because they maintained a steady state of liquid refrigerant in that evaporator coil. They maintained a set amount of saturation. That refrigerant boiling from liquid to vapor. It had a valve that opened and closed so the outdoor temperature didn't have nearly the effect on it. It couldn't measure how much saturation is taking place, but if we knew we wanted this much saturation, it could measure this much superheat. And if I maintained this much superheat, I know that I have this much saturation. So those valves simplified things a lot. But those valves did not control pressure. None of the metering devices controlled pressure. The pressure changes constantly with my conditions. But that boiling from liquid to vapor was essentially the most important part. Now that we understand that, we need to talk a little bit more about pressures. In the field, you're going to hear people talk about what pressure should be. There's only two ways I know of to find out what pressure should be. The first way is when they test equipment. They have a set condition that they test all condensing units at, and a set condition temperature and humidity of all the indoor conditions. At those set conditions, they end up with what they call a 40-degree evaporator coil. Under these laboratory conditions, we know exactly what the outdoor pressure will be and exactly what the indoor pressure will be. And with a variety of different refrigerants, it's usually still at a 40 degree. Now that 40-degree saturation is only going to be where liquid and vapor both exist at the same time. So if we have a TXV, ideally right here, most of this coil is going to be at 40 degrees. Beyond saturation, that temperature will start to rise. So in a laboratory conditions, we know exactly what our pressure is going to be. A lot of people take those laboratory conditions and try to apply them to a varying lifestyle. Even if you had a customer that could maintain a set indoor temperature and humidity, the outdoor temperature is still changing. So having these set pressures is just not practical. The second way of knowing what your suction pressure should be is an app called MeasureQuick. MeasureQuick takes into account many different variables such as return air wet bulb, supply air wet bulb, outdoor air temperature, line temperatures, and it does a whole lot of calculations to find out what your suction pressure should be at within a range and what your head pressure should be at still within a range. We're going to talk later on about many of the little different numbers individually that app uses to find this one number. And then eventually we're going to introduce you to the MeasureQuick app, and by that time you'll have a full appreciation for everything it does. I find that people get overwhelmed with that app using it too soon, so if you're not ready for it, hold off a little bit and we're going to get you there. Now that we understand that there's not a set pressure, let's introduce you to another type of metering device. This metering device is called an AXV or AEV. That stands for automatic expansion valve. Coming into the side is going to be our liquid refrigerant, and then coming out the bottom is going to be our saturated mixture. So this is our metering device. It restricts it from a high pressure liquid to a low pressure saturated mixture. It allows for expansion of that refrigerant coming out the other side. This valve works differently than all of the other metering devices that we've talked about. This valve maintains a constant evaporator pressure. This is the only metering device that will maintain a constant evaporator pressure. So I hear people say that your pressure should be, I'm either thinking, do they have the Measure Quick app, are they working in a laboratory, or do they have an automatic expansion valve? And it's very unlikely for it to be the third option, because you don't see these installed on air-cooled systems. These are installed specifically on equipment that has a constant load, such as a custard machine, or if you have a wine cooler. The temperature of a wine cooler very rarely changes. You take a bottle out occasionally, put another bottle back in, but it's designed for very constant load. I've even seen them on refrigerator systems and a multitude of different things that has a constant and steady load. And HVAC, our typical loads here are going to vary constantly. But this is the only metering device that has a set pressure. At the top we have an adjustment knob, and I can adjust this for whatever pressure I want. For example, if I had R410A, I could set it for 121 psi gauge, and that would give me a 40-degree saturated temperature. But it's only going to be 40 degrees where it's liquid and vapor together. It'll maintain the coil at 121 psi, but it doesn't mean that whole entire coil is going to be liquid vapor mixture. It won't be at 40 degrees. Let me explain. If I installed this system on a regular house AC, and the system was near design conditions, and I adjusted this perfectly, it's possible that I could have this much saturation, and most of this would be at 40 degrees in those lab conditions, and everything would be good. But let's talk about when those conditions change. Let's talk about the system had been off for a part of the day, and you're trying to cool the house back down. This is what we call a heavy load. The return air temperature goes up. Now typically when the return air temperature goes up, the suction pressure is going to go up also. But this metering device is going to keep the suction pressure at 121 psi gauge. So what it does is this metering device closes. As the pressure is trying to go up, this metering device closes and lets less refrigerant in. So it's keeping it at a 40-degree coil, but only where it's saturation. Because this valve is closing down, I end up with less liquid refrigerant coming into my evaporator coil. So my saturation may only be right here. Only this little bit is boiling refrigerant from a liquid to vapor. So because there's only that much boiling it from a liquid to vapor, all of this is superheated vapor. A lot of sensible heat, but very little overall heat absorbed into my refrigerant. On top of that, with a high amount of superheated vapor, I end up with not as much refrigerant to cool my compressor. Now, if I'm only boiling this much refrigerant from a liquid to vapor, it's going to take a long time to cool that house back down. So on that varying load, this isn't going to work very well. Let's talk about a condition in the other direction. Let's say that the customer drops the temperature of their house down. The lower you drop the temperature in the house, the lower that suction pressure is going to drop as well. Let's also add maybe an airflow restriction, like a dirty filter. Now I have less heat coming across my evaporator coil. So that means typically my pressure starts to drop. But this metering device is going to try to let more refrigerant in to maintain that higher pressure. So this metering device is going to open. It's going to let more refrigerant coming in to try to keep it at that 121 psi gauge. Now by doing that, we end up with more liquid in the evaporator coil. So remember, now I have less heat against my evaporator, and now I also end up with more liquid refrigerant in my evaporator. So what will happen is I'll end up flooding my evaporator. All of this could be at saturation, liquid and vapor together. So here I could still be at 121 psi gauge, but all of this is liquid refrigerant. I have 0 degrees of superheat. With 0 degrees of superheat, that means I'm getting liquid refrigerant all the way back to my compressor. Even though this metering device would maintain 121 psi gauge, it doesn't tell us how much refrigerant's maintaining in that coil. We may not have enough refrigerant to cool it effectively, or we could flood that evaporator and flood the compressor because it's letting too much refrigerant come through. So trying to maintain a pressure alone for varying conditions doesn't work. However, if my load is constant, such as that wine cooler, a nice constant steady load, this guy's going to keep a set amount of suction pressure. This is going to be cheaper than a TXV at a nice constant conditions. But in HVAC, those conditions are never a nice constant conditions. So this is the only metering device that will keep a constant suction pressure. There is another device that helps control suction pressure called an evaporator pressure regulator. A lot of times people will get these mixed up. The automatic expansion valve is a metering device. An evaporator pressure regulator is a device that goes in the suction line that helps build suction pressure. It keeps a minimum of a suction pressure of X, Y, and Z. This is also going to be a commercial component, typically with multiple evaporators. You put this on the higher temperature of the evaporators, and it keeps the suction pressure high enough into a range for its normal operating. The evaporator pressure regulator will keep the pressure at a minimum of a number, but it will allow it to go higher than that number. But it's not a metering device. The automatic expansion valve is a metering device, and it will keep the evaporator coil in a range. Now they make two different kinds of these. They make one kind that's internal, that's what this one is. It's measuring the suction pressure here. And they make one with an external equalizer, just like a TXV, that has a third tube coming over here to this point. So it's measuring the suction pressure here. The larger that evaporator coil is, the more likely that you could have a small amount of pressure drop. So it's more accurate reading it over here at this point. But either way, the automatic expansion valve works the same way of keeping a set pressure in that evaporator. So I want to put up some flags of caution for you. We know that the automatic expansion valve is the only metering device that maintains a suction pressure. We know that at laboratory conditions, the only way you're going to have a set non-changing pressures. We also know that the MeasureQuick app is one of the few ways that you're going to be able to see what those different pressures are going to be at different conditions. But as you go through this trade, you're going to meet many people that are going to be only concerned with your suction pressure and high side pressure. They're going to be saying, hey, what's your suction pressure? Or your suction pressure should be X, Y, and Z. I need to throw up a flag of caution. Those people have either overly relied on that shortcut, or they were taught it that way and they think that's the only way it is. Many of us have learned something one way, and it's very difficult to unlearn it to learn a new way. A lot of people get very defensive. I learned it that way, that's the only way it is. So I'm throwing a flag of caution for you to be very careful how you engage this person. Typically ask some baseline questions. Is it always going to be that number? So try to see how they respond to those questions. If they respond of, well, or I don't know, fantastic. Now you can start asking more questions and you can see where you go. But they start getting defensive, like, no, it's always that number. And they start giving definite answers. They start locking up, or their body language starts to change. Stop, immediately stop. Change the subject to something else. You'll still have questions, but write those questions down in a notebook and then look them up later. It doesn't mean that person doesn't have a ton of stuff that you can learn from. What it does mean is that person gets very defensive. As you're questioning their methods, they feel like you're questioning them as a human being. And so people get very defensive of that. And it's very difficult to explain the difference. So change the subject onto something better, something they do know about. And also, don't judge the person. Just because the person has learned with pressures alone doesn't mean that they're not very smart, and doesn't mean they don't have a whole lot to offer. These people have tons and tons of information and tons of knowledge to share with you. So stay on the good side of that person, because you never know when you're going to need them to bail you out. You're going to be on the phone with a problem, and they have the key. They have the answer that you're going to need. So be very careful not to upset that person. Ideally, that person will be more curious and wanting to learn and be wanting to share that information. But if they're not, don't push them. Still try to keep them on your good side, because there's still a lot you can learn from that person. Ideally, over time, if you make a rapport with them, you can start leading into some more and more questions and asking about, hey, I read this in this book and it explains this. And sometimes they'll say, oh, that book stuff doesn't apply. Those always worry me, because the book stuff does apply. It's just a different vocabulary. The book stuff is a way for people in the past and engineers to explain how they design something. Just like I'm talking to you now, the books are simply words that communicate to us. People say, well, in the field it's not that way. But technically it is. It's the same information, it's just different vocabulary used. So just throwing that little word of caution. You may never see an automatic expansion valve, but now if you do, you'll understand what it's for. You understand with an automatic expansion valve, we don't do superheat at all in this system. We do want to charge it by giving it enough subcooled liquid, or if it's commercial, a clear sight glass or the proper amount in our receiver. But next, let's cut this guy open and see how it works. In our simplest form, liquid refrigerant comes in through our liquid line, and right in this chamber there's going to be a hole and another fitting right here. What's happening is that is our metering device. That is what's metering the refrigerant. The size of this hole is going to change because there's a little cone right here that shoves into that hole. And as this plate moves back and forth, it adjusts how much refrigerant is coming through this hole. Here is our low pressure side where we have our pressure drop. And from there we continue on out the bottom, and that's going to our evaporator coil. So our metering device is in its simplest form right there. Now if you notice, there's a spring here pushing up on this piece. We have another spring on the top side with an adjustment screw. So when we adjust it, we're really just adjusting the pressure against this spring, which goes against all these pieces here. Now, we got to get the tension from here back to this spot. So right here we can see this cone shape. That cone shape fits into this little groove, or this little hole right here. With this cone out of the way, the refrigerant flows straight through here, through this hole into the suction side. What we do is we shove this cone up into that hole, and it changes the size of that hole. Notice it has this ring around here. That's where the spring pressure pushes up on the bottom side. And notice the gap here, and then again on the other side here. So as the refrigerant's coming down, it goes around this plate and it continues on. So this is by design, this ring around here. So this spring pushes against that ring. Now this cone shape is what's moving into and out of that hole, so it changes the size, controlling the flow of refrigerant. But there's a little bit more to it than that. On this side, on the flat side, we have the spring on the bottom, but also on the top side we have something very important. If you see right here, there's a pin in right there. That pin, also known as a rod, travels through this whole system on the back side and is connected to this plate here. On the other half that's cut open, you can see it has a pin or a rod here as well. So we have a pin pushing on both sides. By having the pin push on both sides, it keeps an equal amount of pressure on both sides of these plates. If I was to only push on one side, it would cause this to be pushed at an angle, and that could affect their flow of refrigerant. So having the pin on both sides helps keep this level as it pushes back against the spring. So let's look at what's pushing on the pin. So here we can see our adjustment screw is pushing against this plate right here, and that example, this plate is here. So we're going to take that out of the way. The spring is now pushing against a piece of metal here. That metal is represented right here, so we're going to take that out of the way. So here you can see the top of the spring, it has this groove in it. That's where the top of this bolt pushes down, adding spring pressure. The other side of the spring fits right around this piece here. And on the bottom, we see that it's completely flat. That complete flat spot fits against a very fine piece of metal here, but we can't see it until we take this piece out. Now that we took that bottom piece out, right here is a very thin piece of metal. Notice how it has this disc, very similar to a TXV. Well, this disc is a type of diaphragm. And what it is, it allows this thin piece of metal to move back and forth. Remember this channel we talked about earlier? Well, this channel allows for my suction pressure to travel up into this space and fill up this gap. By having this thin piece of metal here, it's welded all the way around, and it keeps the suction all on this side. In other words, it keeps that suction pressure from entering this top part of this valve, because there wouldn't be much keeping it from leaking out of the threads here. So this plate being sealed keeps the refrigerant held in. Also, this plate being thin allows for it to move. So this plate moving is very important, but this plate has to be thin enough to allow it to move. So what's cool is we use this thicker metal here to handle the spring pressure on the top side so it doesn't tear the plate. And on the bottom side, we use another thicker metal here on the bottom side, so as this piece moves, it's applying the pressure to the top part of this piece of metal here. Now if you notice, this thicker piece of metal here has this groove cut in it. Well, this groove is done by design. It keeps this square inside of this chamber. So having this little groove in here allows for it to move up and down without getting sideways or without this piece of metal jumping off to the right or left and getting hung up. It also has these little manufacturing grooves in the side to keep this in track and in place as well, which is pretty cool. You can see what is this plate pushing against. So as this plate pushes down, it's actually pushing down against these pins or these rods. So we can see this rod here, and as I push it up, you can see it travel up right here. So now I'm going to push it back down. You can see the rod come back out the bottom. And if I push it up from the bottom, you can see it come back to the top. This rod simply moves back and forth. But see how thin this metal is? If this piece of metal was pushing against the rods, it would wear a hole in that metal pretty fast. So by having this thicker piece of metal in its place, it allows for this thinner plate to evenly distribute its pressure across this thicker plate, and that thicker plate can handle the pressure of these pins on both sides. On the top side, we put a thicker plate as well, and this thicker plate is able to handle the pressure of the spring, and then above the spring, we have this that's able to hold the spring in place and be able to handle the pressure from this adjustment screw. So it's pretty cool how this keeps it all separate. These two pins are pushing down equally on this ring here on each side. So the pressure here on this spring pushes down on the pins to force this valve open. So as we increase the pressure here, more pressure on the spring, more pressure against this plate, more pressure against the diaphragm, more pressure against this plate, which means more pressure on our pins, and our pins put more pressure on this disc, which pushes pressure against our spring and causes this valve to open. If I decrease the pressure here, it decreases the pressure on the spring, which is less push against this plate, which is less push against the diaphragm, which is less push against this metal here, which is less push against these rods, and now this spring pressure can overcome it and start to force it closed. So these two springs work against each other. Once we have it set, they're essentially balanced. What breaks the balance is going to be the suction pressure right here. So as my suction pressure increases or gets too high, the pressure in this chamber here travels up through this tube, and it works with this spring pushing up against this diaphragm or against that plate. Now this spring pressure takes over and it pushes this closed. Now as my pressure starts to drop, I end up with less pressure pushing against it. So this spring takes over and it pushes against this rod, against the diaphragm, against this plate, against these pins, and that pushes this back open more. So this thing is just constantly moving back and forth, adjusting to maintain the pressure at whatever you set it for. I find the engineering behind this absolutely fascinating. So it's essentially, we have three pressures. We have our spring pressure pushing down on the plates against the pins, forcing the valve open. We have this spring pressure that's always pushing up against this pin, against this cone, the metering device, to close it off or to reduce the pressure. So these springs balance them out, pressure 1, pressure 2. And then third pressure is our actual refrigerant pressure. And that's what's essentially breaking the difference between the two springs. So the little bit of difference between this tube right here, the pressure in this tube, overcomes and changes it to where it maintains a constant pressure. So if I set this for 120 psi, anything less than 120 psi, this spring will take over and will push this open, overcoming the spring pressure. Anything above 120 psi, the pressure pushes up on this tube, works with this pressure, and it pushes this up. When this gets pushed up, the spring pushes this closed. And as the pressure starts to drop down, then it allows less pressure here. This spring overcomes this spring, and now it pushes this valve back open. So it's opening and closing, opening and closing, opening and closing. Pretty cool how this works. As you can see, getting dirt or debris in here is going to be an issue. So if we didn't braze with nitrogen, any of those flakes in here, if we had anything we left debris in the piping, if we didn't cut the copper correctly, any of those debris can stop up our metering device here, it can stop up our tube here, it can get up in all of our moving parts here, it can get around where the pins are here. So we want to keep all that debris out of these moving parts. But I find these absolutely fascinating how they work. It's quite a simple design overall. Many different brands, and this one's what we call internally equalized. So the pressure right here, right after my metering device, is what's affecting it. Other models will have a hole drilled right here. Many people call it a third port, but it's really an external equalized. So the tube on the exit of the evaporator, that's going to be the pressure coming into this tube that's affecting what's happening here. I typically prefer those, but the engineer who designs it, he has the final say. He's designed it for a specific reason. Now in these particular models, we also have this plastic cap that goes back on, and that helps keep the dirt and debris out of this thread sealant. Other models have a very fancy cap that they can unscrew, and behind that is your adjustment. There's many different models. This is just the one that I was able to have access to cut open, but that is how it works. It's pretty simple, pretty cool.